Hello everyone, welcome back. Today we'll be starting a chapter on alkanes, and alkanes are the simplest hydrocarbons. As you know, most of the hydrocarbons are derived from fossil fuels by extraction from natural resources, and alkanes are the simplest of all the hydrocarbons. And as you see here, they don't have any reactive functional group. That means they are almost chemically inert and they have to be transformed to another active functional group. So basically, chemically, they are found to be less reactive. As you say, most of the hydrocarbons, they contain carbon-carbon or carbon-hydrogen bonds. Those are the only sigma bonds that present in hydrocarbons, especially in alkanes. So the name alkanes refers to hydrocarbons, the simplest hydrocarbons, and mostly they only contain carbon-carbon or carbon-hydrogen bonds. They can be found as a chain or also a cyclic form. So they could be acyclic, or they could be also cyclic compounds. So based on what I just described, they only contain carbon-hydrogen bonds. Excuse me. So for the open one, for the chain one, generally they are described by Cn, that is carbon number, hydrogen, carbon number times 2 plus 2 is a general formula. For example, if you have a 6 carbon chain, 1, 2, 3, 4, 5, 6, you will have 14 hydrogens for an open chain alkane. This, by the way, is called hexane. So A-N-E refers to all of the alkanes that are in this general class of chemicals. So if you have a 5 carbon chain, it will be C5. 2 times 5 is 10, 10 plus 2 is 12, so it is a C5H12 compound. So this general formula is applicable for all alkanes, regardless of their chain lengths. But if you have a cyclic compound, which is alkane, which is only containing carbon-hydrogen bond, the general formula is CnH2n, because when you bring one end of the carbon to another end of the carbon, you have to lose at least two hydrogens. Therefore, if you want to form a cyclic alkane, this is called cyclohexane, because there are 6 carbons. So C6, number of carbons, 2 times 6 is 12. So it is a C6H12 formula. So C6H14, which is hexane, an open chain, and here is a cyclic compound, a hydrocarbon, which contains only carbon and hydrogen, always is defined by CnH2n. For example, if you have a 5-member ring like this, a cycloalkane, which is called cyclopentane, this is 1, 2, 3, 4, 5 carbon, C5. So if you have C5 here, 2 times 5 is 10, so the hydrogens should be exactly 10. If you just count them, 2 hydrogens here, 2 hydrogens, 2, 2, 2, there are 10 hydrogens. So in general, as a review of alkanes, which will go in detail in the next section, you need to understand they are the simplest hydrocarbons. They are almost non-reactive. They only contain carbon, hydrogen, and carbon-carbon bonds. And they could be straight chain, or they could be a branched chain. And also a major difference would be with the cycloalkanes. So these are called cycloalkanes, and these are just alkanes. So within alkanes, there are also cyclic ones. That's what you need to understand. So in the next section, we'll go in detail how the bonding happens and also some of the representative alkanes that are present in this group. Continuing our discussion on alkanes, which are hydrocarbons that are the basic units of any organic compound. We start with the smallest molecule, methane. Remember, we have a formula where you have the number of carbons. If you have 1, 2 times 1 is 2, 2 plus 2 is 4. For fully saturated hydrocarbon alkanes, this is the formula, and CH4 is the smallest, which is called methane. You have a tetrahedral carbon, which is C at the center, and 4 of the hydrogens. So methane is the lowest in the alkanes series. The next one, you have C2H6, which has CH3, all sigma bonds, is called ethane. The third one is C3H8. If you just put 3 here, 2 times 3, 6, 6 plus 2 is 8. C4. So it continues like that, where everything is just addition of one more carbon with 3 hydrogens. For example, the next ethane in methane is just a removal of one of the hydrogens but replaced by another CH3 or methyl group. So the next one also is addition of one ethyl group. The next one is addition to the methane, additional of one propyl. But the fundamental structure where it goes to have a carbon at the center and another hydrogen here, one hydrogen. We have already discussed that these are made of sp³ hybridized carbon. This weight shows you the hydrogens are now coming out of the board, and this hydrogen is going into the board. So this is a fundamental structure for almost all of the alkanes. The carbon is 1. You have to remember it is a sigma bond that exists between a carbon hydrogen is a sigma bond. The next important characteristics you need to remember would be the carbons. All of the carbons in alkanes are sp³ hybridized. That means there are 4 equivalent lobes of sp³ hybridized. 4 meaning the sp³1, sp3, sp3, sp3. There are 4 sp³ hybridized orbitals that make bond with hydrogen to form a sigma bond. So this is a fundamental structure you should always be able to write comfortably. You have a central carbon, one hydrogen is going in, the other hydrogen is coming out towards me, and these 2 hydrogens are always on the plane of the board. So that's how you would be drawing. For example, if you were to draw for ethane, ethane would be just addition of one CH3 by just removing one of the hydrogens. So the structure would look like, for ethane, you have C. Of course, the hydrogen still would be kept. And this hydrogen now is replaced by one more carbon here for ethane. So that carbon is this carbon. And you always draw that this is on the plane of the board. And you have one hydrogen that is out of the plane of the board. One hydrogen is into the plane of the board. And this hydrogen will be satisfied. So the structure should always keep the tetrahedral geometry at each carbon. So if we were to draw propane, for example, it's just a removal of one of the hydrogen and replacing it with another CH3 to form propane. So in general, you should be familiar with a drawing by just, it is already known that for butane, for example, you have 4 carbons. So carbon 1, 2, 3, 4. So this is equivalent also to saying that you have 3 hydrogens on this, CH2 right there, another CH2, another CH3. So this is butane, which is C4H10. This is ethane, C2H6. So the important concept I want to impart on you would be that all of the alkanes, they are sigma bond, because it has an implication when you have a sigma bond versus a pi bond, because the reactivity of all of the alkanes or hydrocarbons comes from what type of bond they have. And also the orbital that made 4 of the hydrogens attached to them is through 4 of the sp³ hybridized carbon. So if you just look at this model right here, the model shows you a 3-carbon compound. The 3-carbon compound is propane. So propane has C3H8, as we know. So each one of the carbons, for example, if you just take that carbon, it has a tetrahedral geometry around it. One hydrogen coming to you and another hydrogen coming towards me, but this carbon and that hydrogen are on the plane, just on the flat plane. These are in and out. So this is an sp³ carbon where you have this CH3. Next carbon is CH2, and it's also still tetrahedral because you have this whole group is coming towards me, and this whole one hydrogen is coming to you, and this carbon and that hydrogen are on the plane of the board. So it is C3H8 structure. I encourage you to practice with a model in better understand the structure of all of the alkanes that you might encounter. So it's very easy. It's just a continuation of each chain. As you see, this is CH3 right here. Next CH2, there are 2, and CH3. So these are the general structures, the general structure for hydrocarbon alkanes, representing here, for example, a 3-carbon alkane, which is a propane. And all of the bonds that made, all of the carbons that are in this chain, the black ones, are sp³ hybridized. There are 4 items that are attached to each carbon. So that's why we have 4 sp³ carbons. So the chain continues like that, and even if it is a cyclic alkane, which we'll discuss later on, the hybridization for the carbon still remains sp³ hybridized. Now let's discuss about isomers of the same molecular formula but different number of hydrogens. For example, if you just take this straight chain pentane, pentane is a C5H12 hydrocarbon, which is alkane, C5H12. So on the board, as you see, I have all of them are C5H12. So from our past discussion, we have said that compounds that have the same molecular formula, but they are differently constituted or differently bonded to one another, are constitutional isomers. So I have here for pentane, pentane has 1, 2, 3 constitutional isomers. So they are called constitutional isomers. They are not the same molecules. They have the same molecular formula. All of them are alkanes, but some are branched, some are straight chain. So it's very important for you to understand. You can write different combinations for different straight chain alkane. So these alkanes are all hydrocarbons. That means all of the carbons are at each one of these are sp³ hybridized, and all of the bonds that are present in this are all sigma bonds. The only difference they have, chemically also and physically they are different, they are differently bonded. For example, here it is a straight chain. Here one of the metal group is actually by just having one more hydrogen becomes CH3 and it is bonded at the center. So make sure that the octet rule is satisfied when you branch out different molecules, and then just count also the bonds that are around each carbon. So if you just look at this, they are different compounds but having the same molecular formula. So there is very important concept in the future that you should know. Each carbon can be designated as a primary, secondary, tertiary, and quaternary carbon. This is very important. I will repeat that. These two carbons, where they are only attached to one carbon, are called primary carbons. This is primary. And this is primary. And the next one, if you just look at this carbon is attached to two carbons, right? One here, one there. So this carbon is called a secondary carbon. This is an important concept when we do reactions, which carbon was reactive or not. Here in this carbon, if you just look at this carbon, it is directly bonded to this carbon and directly bonded to this carbon. Therefore, this is also a secondary carbon. And if you just look at this one, this is also a secondary carbon. Now, let's come to this one. The more branches you have to be careful. Your carbon would be not primary, or it might be even tertiary. So as you see, this carbon is attached only to this carbon. Therefore, this metal group at the usually at the outskirt would be a primary. But this carbon right here is a secondary because this is attached to two carbons right there. Okay, pay attention to this one. This one is attached to this carbon, 1, to this carbon, 2, to that carbon. So this one particularly is a tertiary carbon because it is attached to 3 different carbons. If you just look at this one is only attached to that, so therefore it is a primary carbon. Now let's come to this one right here. If you just look at this carbon right here, it is a primary carbon because it's only attached to this carbon. If you just look at that carbon, it's also primary carbon. If you just look at this carbon, it's also a primary carbon. If you just look at this one, is a primary carbon. But remember, this one is attached to one carbon here, 2 carbon, 3 carbon, 4 carbon. This carbon is called quaternary carbon. A quaternary carbon. This is called quaternary. Quaternary. This is called a tertiary. These are called secondary. Secondary. And these, the ones which are only attached to one carbon, are called primary. Remember now the concept: primary carbon, secondary carbon, tertiary carbon, and quaternary carbon. So those are important in understanding the different constitutional isomers of an alkane. 2 things now. An alkane can be a straight chain or branched. So here you can branch it into this. Still it is a C5H12. Here you have a C5H12. It's still highly branched. So that is all of this pentane has 3 constitutional isomers. So in some problems you could be asked to write out all constitutional isomers for a given alkane. So you need to practice to have those constitutional isomers. One other thing I want to tell you would be these straight chains are always called with N, normal pentane. For example, for pentane, for the straight chain, this is called N-pentane. What we are saying is normal pentane. If somebody tells you normal hexane, normal heptane, normal octane, it means that they are straight chain. Other than that, this one have a naming, which I will give you in detail what it means. So this pentane with the branched one, this one, is called 2-methyl butane. 2-methyl butane. Now let me explain this. The 2 position, 2 tells you where the methyl group is. First of all, you should identify what is the longest chain possible in this compound. The longest possible chain is 1, 2, 3, 4. That is straight. So that would be the butane. That is the base. But at 2 position, if you just count it from here, 1, 2, at 2 position I have a methyl group. Methyl is a substituent. So now in the naming of this compound, 2-methyl butane, you have a butane structure, but at 2 position, at carbon number 2, you have 1, 2, 3, 4, that's carbon number where they are. At position 2, I have a methyl group. That's why it's called 2-methyl butane. How about this one? If we were to name this, the straight chain, the longest chain that can be counted would be 1, 2, 3. Therefore, the base would be propane. So I would just write propane, but at position 2 of propane, you have 2 methyl groups. So how do you name them? You would say 2,2-dimethyl. 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 2,2 represents that there are 2 methyl groups. That's why we have a di. There are 2 methyl groups on position 2. So 2 still refers to 1 methyl, another 2 refers to. So you need to write both of them. 2,2-dimethyl propane. So in the naming we'll just discuss later on, but I want to give you one more example of for not pentane, but for example, if you have a hexane type compound, so if you have something like this is an example with how many carbons? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons could give you a lot of different constitutional isomers possible. But in any case, this is an 8 carbon. So chemical formula would be CH8H18. If you just do the math with CnH2n plus 2 formula. But how do you name this? So to name this, now the longest chain is 1, 2, 3, 4. Now I have to check 1, 2, or 1, 2, 3, 4, 5. So the longest chain would be 5 carbon. So the base would be pentane. So if I have this, if I just do this, 1, 2, 3, 4, 5. So it is a pentane base because it's a 5-carbon long chain. But at that position, in the long chain of this, if you just take this is a chain, there are 2 substituents remain. Okay, this is how you do it. You first outline which one is the longest chain, outline it like this, and then you are remaining with these 2 things. These are called the substituents. So the substituents are, let's say, always you have to give the lowest number. So this is at position 2. So at position 2 you have an ethyl group and a methyl group. CH2CH3 is called an ethyl group and a methyl group. So you have to always write it in alphabetical order as well. So 2 ethyl, again 2 methyl, pentane. So the name of this compound would be 2-ethyl E, because E comes first and M comes next, because alphabetically also you have to be careful how to write the substituent. At 2 position, both are on 2 position, both are on this carbon. At carbon number 2, if you were to count 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, on this chain, at 2 position, both substituents are at 2 position. Therefore, it will have 2-ethyl, 2-methyl, pentane. Pentane because it is a 5-carbon. So we'll discuss this and we'll practice as we go along in our next discussion. Before we proceed to cycloalkanes, I want to review back what we have done for alkane chains. So be familiar with the naming. Butane, for example, is a C4H10 compound or hydrocarbon. Pentane is C5H12. Hexane is C6H14. Heptane is C7H16, and so on up to decane. At least you need to remember a 10-carbon is decane. Octane is an 8-carbon hydrocarbon, so C8H18. So the formula comes from, I have already discussed this, CnH2n plus 2 for the number of hydrogens. So if you have 4 carbons, it would have 10 hydrogens. 4 C4, 2 times 4 is 8, 8 plus 2 is 10. That is the formula for alkanes. As we have already discussed before, pentane had 3 constitutional isomers. That means they are not the same molecules, they are different physically and chemically, but pentane, the normal pentane, and pentane can have, or similar to C5H12, you can have 3 different isomers. And as you go along, hexane, for example, could have 5 different isomers. And heptane could have up to 7 constitutional isomers. So what I like to do is, I want you to exercise on the possible constitutional isomers. Those are unique isomers, and you have to prove that they are unique by just the naming. So when you try to naming by IUPAC way of naming, they shouldn't give the same names. That means you have reached to the limit of with a number of constitutional isomers. For example, if I have a compound like this, 1, 2, 3, 4, 5, and something like this. So you should be also familiar now with the stick form of writing the alkanes. This compound has 7 carbons. So it is a C7 constitutional isomers. So C7 should have C7, 2 times 7, 14, 16. So this is a C7H16 formula. So if you remember, I already told you, if you have C7H16, you could write at least 7 different constitutional isomers, 7 different compounds, that means. So you need to practice where you have 7 different, unique, different compounds. So let's again practice the naming of this hydrocarbon with 7 carbon. So let's just look at what is the longest chain. The longest chain, uninterrupted chain, would be 1, 2, 3, 4, 5, 6. 6 carbons is the chain, can be written as 6 carbon. So the base for this naming would be, remember, would be hexane. So don't make any mistake, because the longest chain in this hydrocarbon, or the straight chain, because of this you cannot say this is not the chain. So this is 1 carbon, 2 carbon, 3, 4, 5, 6. So here is your 1 carbon substituent. This is called substituent. At what position? So 1, 2, at 3 position. So this is carbon number 3. So the chain is actually going all the way, you are counting it this way. This is the straight chain. But right here is the substituent. The substituent is at 3 position. On carbon number 3 you have a substituent. The substituent is 1 carbon. That 1 carbon substituent is called metal. As a substituent, remember now, substituents and full compound like CH4 is methane. That's the whole compound as a stable compound. If you have CH3, CH2 and CH3, CH3, that's ethane as a compound. But as a substituent like this, as a substituents on the side chain, they are called methyl, ethyl, propyl. These are substituents. So at 3 position I have a substituent with 1 carbon. That substituent is called metal. So this compound is actually a 3-methyl hexane. This is 3-methyl hexane. So that's how the naming works. So remember now, identify and practice to write exhaustively all of the constitutional isomers that are possible. 1, for example, you take C8H18, that is, you start with a straight chain of 8 carbons, and then you start to branch it. So each possibility of branching would give you different compounds, and start to name them as well. So the name should be unique, so that now you know exactly you have different constitutional isomers. So I have here a 3-methyl hexane compound. So now we'll continue with cycloalkanes. That means compounds with cyclic structure, and still they are alkanes or hydrocarbons, straight with sigma bonds as well as sp³ hybridized carbons. So next discussion would be on cycloalkanes. Let's start by discussing cycloalkanes. General cycloalkanes, meaning that they are in cyclic form, so they are not very different in terms of the type of bond. They have all sigma bonds. Again, I will repeat, they have carbon hydrogen, carbon carbon sigma bond, and also the carbon is, all carbons are sp³ hybridized, the same as like the straight chain ones. So the smallest or the simplest cycloalkane is cyclopropane. You can only make a ring with 3 carbons. That's the lowest you can do. So cyclopropane, remember now, propane in normal propane is a chain, but here you start by saying cyclo. Cyclo to show that this compound is a cyclic structure. Next one is butane, but in this case 4 carbon, but a cyclobutane, a cyclopentane, and a cyclohexane, a cyclooctane, cycloheptane, cyclodocane, and continues. So the ring size becomes large and large and large. So the general formula for cycloalkanes is CnH2n plus 2n. Remember, for alkane, the straight chain, the open ones, we had plus 2 here. But for cycloalkanes, for example, if you have 3 carbons, 2 times 3 is 6. So there are 6 hydrogens. Here C4H8, because you have carbon 4, 2 times 4 is 8. C5H10, C6H12. It's just double of the number of carbons. Because since it is a cyclic form, there are 2 hydrogens that are out in making the bond. So as I said, all are sigma bonds, all are sp³ hybridized. For example, if you just were to look for this compound with 6 of the hydrogens, what it means is this is the central carbon, this bond and that bond are on the plane of the board, but one hydrogen is in and the other hydrogen is coming out. So this particular carbon is sp³ hybridized. sp³ hybridization. So all of the carbons would have the same thing. So this bond is on the plane of the board and that bond is on the plane of the board. So one hydrogen can come up towards us and one hydrogen would go in. So all of the structures look like one hydrogen out, one hydrogen in. One hydrogen on this case would be in to the plane of the board and another hydrogen coming out. Here again, if this and this are on the plane of the board, one hydrogen is out and the other is into the plane of the board. Here as well, one hydrogen is out into the plane, out of the plane of the board, and one is into the plane of the board. There are 12 hydrogens on this because it is C6H12. So be familiar where the hydrogens are, because mostly we don't give you the hydrogens on this kind of structure. But remember how actually they look like, how the hydrogens are displayed on this. Similarly to the alkanes that are the straight chain ones, cycloalkanes also have constitutional isomers. That means compounds with the same number of formula or the same formula but different way of arrangement. For example, if you have a C5H10 compound, which is this one, which is cycloalkane, you could write about, I believe, about 5 different structures with still C5H10. For example, let's start with 3 carbon. If I have 3 carbon in the cycle, there are 2 carbons that are out. So this is still C5H10. Ethyl group as a substituent, 2 carbons as a substituent. I can have also a 4 carbon cyclobutane and 1 substituent, which is still C5H10. And I can have also a cyclopropane with CH3 and CH3, 2 carbons plus 3 is 5 carbon. This is still C5H10. It doesn't mean they are the same compounds, but they are constitutional isomers. But you could be able to write from C5H10, 1, 2, 3, 4. The other one can be, for example, you can write CH3 here, another CH3 somewhere else, not on the same carbon, like that, but this is still C5H10. So when we say cycloalkanes, they are in cyclic form, they have all sigma bonds, and they are sp³ hybridized carbon. And the formula for them, the number of hydrogens, is CnH2n. Similarly, they have constitutional isomers, that means different isomers, where you have a different way of arrangement in the carbon-carbon bond, and they are all different compounds. You have two metal groups on different carbon. You have two metal groups on the same carbon. You have one metal group on butane, and you have two carbons out on the same carbon that are a chain as ethyl group, not a metal group, two carbon as a substituent. So this is a normal cyclopentane. So overall we have 1, 2, 3, 4, 5 different constitutional isomers for C5H10, which is a cycloalkane. This is starting from cyclopentane, for example. This is the base is called a cyclopentane. So we'll continue next time with nomenclature in detail of how to name. When we say nomenclature, how do you name organic compounds starting with alkanes? So that will be our next discussion.